I will start with my pet problem, which is problem 942. And I realize that 942 is solved in your book, but there is so much more to it than just 942. But there's so much more to it than just this solution. It is a key problem, it has a canonical pendulum, and I want to spend quite a bit of time on it in the hope that I'll give you some insight that you may not obtain otherwise. There's a bob M here hanging at the end of this conical pendulum. The length is L. Let this point be P, and let this point be M, and let the radius of this circle be R. The angle is theta here. I can put in all the forces at point M. There is here mg down, and there is the tension up, and that's all there is. There is nothing else. I can decompose the component T in a horizontal component, which is T sine theta, which, by the way, is the resultant force. Resultant force, it is the net force. It is a vectorial sum between these two, and you can clearly see that because if I take the vertical component of T, which would be T cosine theta, then this one must cancel out this one because there's no acceleration in the vertical direction. There is then a circumferential velocity v, and that v equals omega r, and the direction of this v vector changes. The magnitude does not change, but the direction does change. Omega, which is the angular velocity, and theta cannot be arbitrarily chosen. They are coupled to each other, and that's what I want to show you first. Let us look at the vertical direction where there is no acceleration. So T cosine theta must be equal to mg. Further, T sine theta, which is this force, must be the centripetal force to make this object go around in a circle, for which I can also write down m omega squared r. And then, of course, r divided by L also equals the sine of theta. And if you combine these three, it should be very easy for you to prove that omega squared equals g divided by L cosine theta. So you see, you cannot arbitrarily choose omega and theta. They are coupled through this relationship. If omega goes up, you want to go faster. Notice that the cosine of theta, therefore, must go down, and that means theta must go up, which is completely consistent with our intuition. For omega to go to infinity, the cosine of zero would have to become 0, and so theta would have to go to pi over 2. So what this is telling you, that if you rotate it around, no matter how fast you rotate it around, the rope will never be horizontal. And the reason for that is obvious, because there's always gravity, that is the force that always tries to make it go down a little. So you never get exactly that string at an angle 90 degrees relative to the vertical. When theta goes to 0, omega goes to the square root of g over L, which is exactly the same angular velocity that you would have if the pendulum were just swinging in a plane and not a conical pendulum. And it's not so obvious that that is the case. That is not so intuitive. Well, I have here some very simple poor man's version of a conical pendulum, and I can rotate this around, and all I wanted to show you is it's rotating around now. Look at the angle theta from above, and if I go faster and faster and faster and faster and faster and faster, you see clearly that the angle theta increases. And that's all I wanted to show you, and no matter how fast I go, I will never get this exactly horizontal. It will always be, theta will always be a little less than 90 degrees. Is angular momentum conserved in this problem? That's a key question. You may even be asked if angular momentum conserved. It's an ill-defined question. Yes, angular momentum is conserved, but only relative to point M. And angular momentum is not conserved relative to any other point that you choose. Not even any other point that you choose on this axis. And that's what the rest of this problem is all about. Let's first go to M. What is the angular momentum relative to point M? And let's first take the magnitude. Well, that is Rm cross P. Forget the cross because they are perpendicular to each other. If I make a drawing from above, here is the situation. Here is omega. Here is point M. If the object happens to be here, this is R of M. And the angular, the momentum P would be like this. It's in the direction of the velocity. So you see, they're already 90 degrees relative to each other. So the momentum, the angular momentum, the magnitude of that equals R, which is the radius of this circle, times mv. But I can write down for v equals omega r, so I also get r squared m times omega. And this, if you please, equals the moment of inertia about the z-axis. If I call this the z-axis, that is clearly m r squared times omega. What is the direction of the angular momentum? Well, the direction of the angular momentum follows from this cross product of r and p, and you will conclude with me that the angular momentum is pointing upwards. R cross p is pointing upwards. So in this figure, I could put in L of m. Here, it's pointing in the plus z direction. Remember that L of m must always be perpendicular to the position vector, and it must be perpendicular to p. Notice also that the angular momentum is completely independent of where the object is in this circle. That means angular momentum is always the same relative to point M. It's always pointing upwards, and that means angular momentum is conserved. And if angular momentum is conserved, there's only one conclusion that you can draw, that the tau relative to point M must be 0. Now, is that true? And the answer is yes, it's true. What is the tau relative to point M? That equals R relative to point M cross F. Well, if we are here, R is this vector from M to this point. That is this vector. What is the force that is acting? Well, this is the net force that takes care of T as well as mg. And that force goes straight through point M. In other words, this must be 0. Because R of M and F, which is this F now, are parallel. The sine of theta equals 0. So yes, indeed, tau of M is 0, and yes, indeed, angular momentum is conserved. There is no external torque about point P, and the angular momentum will always be in this direction, and it is conserved. Let's now go to point P. What is the situation of the angular momentum relative to point P? Well, that is R relative to point P cross P. Don't confuse these P's. This P is this point, and this P is the momentum. And it's immediately obvious that the magnitude of that, so I take the magnitude of this, equals L, which is now this thing, times mv, which is L times M times omega times R. And since I also know that R divided by L equals the sine of theta, I can eliminate the L and I can find that it is M R squared omega divided by the sine of theta. And you see immediately that this is larger than the magnitude of the angular momentum if you choose it relative to point M. It is larger by the factor 1 over sine theta. And how about the direction? Well, the direction is also very different. If this angle is theta, and if this is r of p, this length is L, this point is P, and if the momentum at this moment in time that the string is in the paper, the momentum would be coming straight to me, you shouldn't have any difficulty to convince yourself that the angular momentum L relative to that point P is in this direction. It's perpendicular to this string and it is also perpendicular to P. Now comes something quite remarkable. And that is if you decompose the angular momentum in two directions, one which I call in the z direction and the other which I call the horizontal direction, is horizontal, then it's very easy to show that the angular momentum in the z direction is exactly the same as Lm was before. Because Lz, I look at the magnitude now, equals the magnitude of Lp times the sine of theta. That's immediately obvious because when this is theta, this is theta. And that again is mr squared times omega. You lose this sine of theta. And so that is the same as L relative to point M. That's the z component. It's pointing up. So not only is the z component pointing up, but Lm itself was pointing up. So you can state here that no matter where you choose your point on this axis, you should be able to demonstrate that the z component of the angular momentum is always the same as Lm, is always the same as I relative to the axis z times omega. But is angular momentum conserved? Absolutely not, because you can clearly see that this vector is going around. The horizontal component, by the way, equals mr squared times omega divided by the tangent of theta, because it is Lp times the cosine of theta. So the vertical component is independent of where you are on this axis, but the horizontal component does depend on where you are on this axis. If you had been somewhere here and you had chosen the angular momentum relative to point Q, you would have found that the vertical component of the angular momentum would be exactly the same as it was before, but the horizontal component now would have here a value alpha. Clearly the angular momentum is not conserved relative to point P. If I look at two situations, namely one whereby the string is like this and the other whereby the string is like this, then I have here Lp at one moment in time and I have here Lp at another moment in time. And so even though the magnitude of the angular momentum remains the same, the direction remains the same. That means dl dt cannot be zero, and so there must be a torque relative to point P which is not zero. And that torque, of course, is very easily found. If you look here at P, the torque relative to point P is R cross F. Well, the tension itself goes through point P, so does not contribute to the torque. So it's simply this position vector R, which has a length L, cross product with mg. So I have to take the perpendicular direction, which would be L sine theta, which by the way is R, and I have to multiply that by mg. So the torque relative to point P equals the L times the sine theta times mg. And for this you can write R times mg. That is the torque. The torque is not zero, whereas the torque relative to point M equals zero. Again, the torque is this force times this arm, Rmg. The direction of the torque right here is pointing towards you, and right here the direction of the torque is pointing away from you. I will make a picture to show you this in an easier way from above. Here is a circle. The object is going around with angular velocity omega. Here is the center of the circle, and here is the radius r. At one moment in time, the horizontal component of the angular momentum, horizontal, relative to point P is like this, and at another moment in time, the horizontal component of the angular momentum relative to P is in this direction. And the vertical component is always the same, it's independent. And what you're going to see now is you're going to have a torque here relative to point P, and you're going to have a torque here relative to point P. And it is this torque that moves this angular momentum vector around. And it is therefore immediately obvious, since the torque relative to point P in the z direction is zero, in other words, the z component of the torque is zero, there is no way that this torque can change the angular momentum in this direction. There is no component of the torque in the z direction, and that explains then why Lz remains constant, no matter which point you choose on the axis. So this torque, so to speak, drags this angular momentum along, while the magnitude of Lz remains constant, the direction of Lz changes. The direction of the horizontal component changes, but the magnitude of the L horizontal remains constant. I said Lz, but I meant the magnitude of the horizontal component remains constant, but the direction changes. Now, if you're very good in math, you could demonstrate, but it may not be so easy, that here dl relative to point P dt is indeed tau relative to point P. Keep in mind that the magnitude of Lp is constant, but that its direction changes. Well, I wish you luck, and if you don't want to do that, that's good too, of course. A complete understanding of this problem will also help you a little bit more to understand the very non-intuitive behavior of gyros. You will see the same thing, that a torque is dragging an angular momentum around. And gyros are one of the most difficult things for students and faculty alike. You better believe me.